Hi, everyone. Thank you for joining us today. My name is Liz Gill, and I am a researcher here at NREL and the lead for the Offshore Wind Technology webinar series that this webinar is a part of. Just want to thank you all first for being here. We're really excited about this webinar and the series. I want to take a moment to thank our sponsors, the DOE Department of Energy's Wind Energy Technology Office, in particular, Maggie Yancey and Rin Ball for being such great support on this project. Just want to make sure that we thank them for all their support here. Before we get started with the kind of the meat of this presentation, I want to go over a few logistics so we can flip to the next slide. So this webinar will be recorded and posted on the NREL YouTube channel and also on the WINDExchange website. So we will let the group that joins today know when those are posted. There will be a Q&A following the presentation. So please put any questions that you have during the presentation and after in the Q&A function at the bottom of Zoom. We're really looking forward to introducing Walt, our speaker today. So we could go to the next slide. So Walt is a principal engineer here at NREL, and he leads the offshore wind research platform. He's worked at NREL for 33 years now. And in 2003, he actually initiated the offshore wind energy research program here at NREL. He studied at UMass Amherst, where he got his bachelor's and master's degree and specialized in energy conversion and with a focus in wind energy engineering. Walt has over 120 publications and 2 patents. We're so lucky to have him as a colleague and really appreciate his willingness to help us with this webinar series. So with that, I'm going to pass it off to Walt for the meat of the presentation here. Thanks, Walt.
Oops, let me go the other way. Thank you, Liz. So I'd like to, thank Liz Gill and Mary Halsey for helping me put this presentation together and working on it with me, and also our sponsors at DOE again for setting this whole thing up and sponsoring the time it took to get this put together. This is really designed to be an introductory webinar on the technology of offshore wind and what we see when we look at it above the water. There's a lot of the structure, a lot of the cost is below the water, but this is focused on what's above the water. So I'll start with that introduction and why we're doing offshore wind energy, why it makes sense for the United States and for the parts of the world. And then I'll talk about probably in more detail what goes into characterizing the fuel that powers these wind turbines, which is the wind, and understanding those characteristics, both in terms of the wind resource itself and then the technology implications. And then the second part will drift into describing the technology of the wind turbine itself and go through the different parts of that. So that's what this is all about. This will be an introduction again. So some of my buttons aren't working, so I'm just getting used to which ones do work to flip the slides, but here we are. The first slide is you can recognize a map of the continuous 48 lower United States. And this is a wind resource map. We see different color schemes relate to the different wind speed based on annual averages. So offshore, the darker blues represent higher wind speeds, and then you can see the yellow colors are the lower wind speeds, and the proximity of these offshore winds to the population centers is apparent, where 80% of the population lives in one of the states that's bordering an ocean or one of the Great Lakes. So we have, that's where the energy gets used. So we want to generate close to where the energy gets used. And you can see by comparison, the other places where it's dark blue or the Midwest, where we have lots of room for wind turbine power plants, and we can power those areas, and through transmission can generate power for other regions, but it's convenient sometimes to not have to build such long transmission lines, and in some cases that may not be possible, especially in some of the more populated areas. So offshore wind creates a great option for looking at that. The winds are stronger offshore, and in populated areas where it's difficult to build large wind farms or solar arrays, which take up a lot of space, we can use the space in the ocean to build larger scale projects. And these create unique economic benefits for communities and revitalize. We're seeing this already, revitalization of the ports along the East Coast and the introduction of new domestic manufacturing options and technologies of offshore, which are less constrained by transportation and construction than land-based systems, which need to transport components under bridges and erect systems with land-based cranes. We can do that with big ships offshore, and I'll talk more about that. So this next slide is really kind of a snapshot or a summary of where the industry is today. And I just said today, but we really took all this data at the end of last year. So we'll be compiling this data as we again as we hit the end of the year. But as of the end of last year, there were over 200 projects worldwide, with a capacity that we tallied over 33,000 megawatts. That number is going to grow close to 40,000 when we add up the projects that were put in this year. The average project size is growing. It's getting up to about 1,000 megawatts. And that's because these developers are taking advantage of the economies of scale of larger and larger projects and turbines and amortizing a lot of that, the equipment over larger projects. 99% of these projects are fixed to the bottom, which means they have rigid foundations that are attached to the seabed, but growingly a percentage of those are going to become floating, which means there's going to be buoyant foundations. And we have several demonstration projects and pilot projects that are underway right now, and that's the number of that percentage between floating and fixed is going to change over time. But floating is a much more nascent technology. Another big trend is that we're seeing the average rating of turbines growing. This past year, if you took all the projects, about 7.5 megawatts was the average turbine size, but really people are putting in 10 megawatt machines. That's what's commercially available right now. And the developers will be using 12 to 15 megawatt turbines by the middle of this decade. And that number is going to probably continue to grow somewhat. And there's a trade-off between turbine size and industrializing that supply chain at a particular level. But generally, the larger the turbine, the more economical the project. And that's why we're seeing that turbine growth. And that translates to larger rotors. Rotors are the component that attaches all the blades to the machine and generates 100% of the energy. Those rotors are about 170 meters in diameter already and are growing to 220 or to 240 meters over this decade, which is the length of 2 football fields. So that's a fairly impressive size. I'll talk more about that as well. That correspondingly, the tower heights have to grow along with the blade length. And so you can, as a rule of thumb, it's not exact, but you can take the length of a blade and add 30 meters to it, and that's how high the hub is off the water. And so for blades like the GE blade, which is 107 meters, adding 30 meters, you've got 140, 150 meter tower. So these are getting very tall, which means we need tall cranes and heavy lift cranes. The drivetrains are one of the areas that we're seeing changes in as we get further out. The direct drive generator is taking over with permanent magnets as the mainstay for that. But certainly there's geared systems still. Even geared systems, though, are using medium speed generators with permanent magnets as well. So there's that's a trend toward those machines which have lower moving parts. And overall, the costs are coming down. And that's what's driving a lot of the policy decisions. But we're going to continue to see higher costs for offshore wind than land-based. But when it comes to deciding what's the best option, proximity to the load is very much a big consideration. And offshore wind is leveraging, and we couldn't do this without some of these industries that already exist, like the oil and gas industry and the subsea cable industries that are helping us, and we're tapping into those industries to develop these new projects. So one of the things that we should note this year is that through the past 4 or 5 years, there's been a substantial commitment to develop offshore wind through the states. And in March 2021, the Biden administration, the federal government, announced support for offshore wind and set a national target to reach 30 gigawatts by 2030. And that's commensurate with the level of policy that's already been committed by the states on the East Coast. There are 8 states that have adopted over 30 gigawatts of policy commitments. And in addition to that, in addition to the target, the US projects are being supported through jobs programs that will develop well-paying unionized jobs, and the investments in the American infrastructure to strengthen those domestic supply chains and enable these projects to be deployed and developed out of significant port upgrades that are happening up and down the East Coast. And in addition to that, there is also support for critical research and development that is necessary to bring these technologies into other regions, such as floating wind turbines or turbines that can survive in hurricane-prone regions. So now I'm going to talk about the resource and how we calculate it and why it's important. So I'm going to talk about the resource assessment, how we get the data, and what some of the important characteristics are for the data. Annual average wind speed, for example, probability distributions, wind direction distributions, and then the diurnal and seasonal variations, which are important for planning the utility and how that generation is going to get used. And then I'll point you to some of where those resource data can be obtained. So first of all, offshore is a little bit different than land because we don't have as many observations to rely on. So we have to rely more heavily on computer models to give us the information, although computer models are certainly what's used primarily now on land because they're just getting so much better. These high fidelity weather research and forecasting model, this is we call WRF, was developed by the National Center for Atmospheric Research, is used to estimate the wind speed over wide geographic areas at a very high resolution. And it takes a supercomputer to run these models. And we can generate data for every 5 minutes of the day. And right now we're using ensembles that are up to 20 years in length. And right now NREL is redoing the data for the entire country using what we call the Wind Toolkit long-term ensemble data set with LED, which is characterizing the wind speed at all regions at a much tighter time scale, and looking at these ensembles to get more accurate data over a much longer record. But even with that data, we need to calibrate it. We do that or validate it. And we validate it through measurements, which are very sparse. NOAA operates a whole buoy system offshore, but those measurements are taken at the surface or near the surface, about 5 meters above the surface. And we need measurements that are at hub height because the wind isn't the same at the surface as it is at hub height. And those measurements are very hard to come by. The picture on the right shows 2 different ways to get that. The Met towers that can be installed in the water are very expensive and difficult to measure, even because the turbines keep getting taller. On on the left of that picture, there's a floating LiDAR system, and this is becoming the mainstay for measuring wind speeds aloft. And but they're still expensive and very sparse, so we don't have that many measurements offshore, and that's one of the biggest challenges. So if we're looking at the data and we calculate, we want to look at a specific site. Every site can be characterized on an annual average basis by these probability distributions. And so the lower right is a distribution of wind speed and the probability of when it would, how strong it would blow over the year. And statisticians will recognize this as a Weibull distribution, or can be approximated by a Weibull distribution. And it's showing on the dotted lines when the turbine starts or cuts in, when it reaches its rated power, that's where it hits maximum power, and then it flattens out and it runs at that level till it hits cutout. And this is a distribution that's actually developed for the Humboldt call area, which is now a wind energy area in Northern California. And the top figure is a wind rose, and you can see that's based on the north, south, east, west coordinates, and shows the directions that the wind comes from. And this shows a very strong northerly component with very little wind coming from other directions, which is usually pretty good for siting a wind turbine. So these annual averages are very important, and probably the most important for characterizing the performance of a project. But there are other variables, including turbulence intensity, atmospheric stability, and wind shear, which we have to pay attention to as well. So the diurnal variations and the seasonal variations are very important for characterizing when the generation is going to happen and understanding how that information, or how that electricity rather, is distributed and integrated into the grid and meshed with the other sources that are being generated. And we have to consider that because seasonally the load varies. You've got air conditioning in the summer, you've got electric heating in the winter, and various other loads that happen from the time people wake up in the morning to the time they go to sleep. So, so you see these variations seem to be fairly consistent. These examples I'm showing you on the left are from Oregon, and they are representative of 5 sites that we looked at up and down the coast of Oregon, starting from the north on site 1, or the lower curve, to the south. So the stronger winds in Oregon are in the south. And then seasonally on the lower curve, these diurnal variations were just a snapshot taking in July. So I drew the dotted line on July, where you see that's a very strong, that's the windiest month, and the biggest variation, by the way, from site to site. But you see that it's very important to know that the month of July will generate more electricity in some of the regions, and that needs to be taken into account when setting up the distribution through the grid. So now I'm just going to mention wind shear, and I did mention this already, but it's very important to know what the wind speed is at hub height. So if we're measuring wind speeds using surface buoys, we're not going to have the right answer to what the hub height wind speed is, so we won't be able to predict the energy generation. So we're estimating that through the models, but we also have LiDAR systems now that can project their sensors up to hub height and above and measure the wind speeds aloft. And that's our main objective, and we need that kind of validation. The models that we're using, the weather forecasting models, also give us that data, but we need to validate that. So the wind shear is very important. It varies from site to site, and it varies depending on the atmospheric conditions. So we're always tuned into that. And then when we go to try to assess where the good sites are, we're looking at these heat maps of where the weather wind speed conditions are strongest. And this is showing an offshore wind map of the state of California. The darker red areas are the areas where the wind speeds are the strongest. You can see there's a cluster in the central coast off of San Luis Obispo, where there's a wind energy area, Morro Bay, that's being considered right now. And also in the north, where the Humboldt Bay wind energy area is being considered. And both of those are excellent wind sites, but you can see on the map how that they vary. So these heat maps will describe the wind, and we can find that data on these resources below GitHub and Wind Prospector. These are live links in this presentation. We'll provide those to anybody who wants to follow up with that. This map is showing 100-meter wind speeds, but we can draw a map for any elevation we need to. So another important parameter of wind resource is understanding the extremes, and weather extremes can affect the reliability of the wind turbines, but also their energy production. So we have to understand how the wind extremes vary. Some of the things that we need to consider are the possibility of hurricanes, and especially hurricane-prone regions, let's say south of Virginia and all through the Gulf of Mexico, where we're starting to consider projects. Extreme winds and wave events. And what this is saying is really that the worst case scenario for a wind turbine may not be just the highest wind speed, but it may be a combination of a high wind event with a high wave event that comes from an odd direction. So we need to consider multiple load cases in order to design these machines and so that they don't fail. And then icy conditions. Sometimes the ice can build up. Sometimes if we're looking at Great Lakes wind, there's ice on the surface, and that has to be considered. Extratropical storms. That means if you're from the east, that's a nor'easter, and those can be very damaging, but they have a much different characteristic than a hurricane, and they have to be considered in their own light. And then extreme heat and cold. As we've observed this past year in Texas, there was events where the turbines in Texas were not outfitted with cold packages that were necessary to keep them online, and the machines were offline until the grid could come back. So those need to be those extremes need to be considered. And then finally, the last bullet really is something. It's a new field that's necessary for us to understand. It hasn't really been studied very much, but climate change may affect the frequency and the severity of these weather events, and it may also affect the average wind speeds as well. So we need to start looking at that and anticipating what that's going to do for future machines. So now I'm going to talk about the above the water projects, above the water wind turbine characteristics, and what we're seeing here is a wind turbine on the right with the major parts labeled. And I think most people would recognize these parts, but I'll just go through them quickly. We have the blade, which is the part that makes all the energy and converts the wind to electricity, or at least it converts it to mechanical energy. There's the hub that connects the blades together, and that blades and hub together form the rotor. The nacelle is the big box. It's like on the modern turbines, it's the size of a railroad car. And then there's the tower that holds the whole assembly up. And then you have a deck where the crew can access and stage some of their operations, and a transition piece that connects the tower to the foundation. In this case, it's a monopile. And this is just showing a Siemens 2.3 megawatt offshore wind turbine, which is now small by current standards. So turbines offshore are bigger than they are on land. The average capacity of land-based turbines was just 2.75 megawatts last year. And if I take the average offshore turbine, it was 7.5 megawatts and growing rapidly. the offshore machines have more complex support structures. They have to, because they're in the water and they have to withstand not just the aerodynamic loads, but the hydrodynamic loads that come from the waves, especially under extreme conditions. And they have to be designed to withstand the marine environment. And I have more on that in just a minute. So first, let's start with the just the basics of what an offshore wind farm looks like. It's very much like other wind farms on land. Multiple machines are connected together and the power is sent to a substation. But on a single machine, we've got this machine in the schematic in the foreground. The wind direction coming from the left side toward the hub, goes through the rotor, and that's an upwind machine. So that means the rotor is upwind of the tower. And that wind passes through the rotor. And let's just giving some examples. For a GE machine that's now rated at about 12 to 13 megawatts, the rotor diameter is 220 meters in diameter. So there's about 10 acres that's swept by that rotor as it's spinning. That means that there's about the weight of the wind passing through that rotor is equal to the weight of the machine every 2 seconds. So it's a very, very large span. It's one of the largest rotating machines ever built by humans. And as that rotor spins, it converts the mechanical or the kinetic energy of the wind to mechanical energy and transmits that energy through a big shaft that sends it to the drivetrain. And then the drivetrain is generally a direct drive generator or a geared system that turns it into sends it to a medium speed generator and converts it to power. So the offshore wind plants can be 1,000 megawatts or more in size, and the peak energy output is comparable to a conventional large power plant, such as a coal or natural gas or nuclear plant. One of these machines, if it's a GE 12 megawatt offshore machine, can power 4,500 US residences. And another little fun fact that I've heard GE say is that one revolution of one of these machines can power your house for 2 days. So, and they keep rotating. So here's the, here's the slide. I just want to talk a little bit about how we adapt these machines. All these machines started out as land-based machines and then evolved. And the evolution means larger machines, but it also means that all these foundations are treated very heavily with corrosion-resistant coatings that were developed over many, many decades by the oil and gas industry to prevent rust and corrosion and compromising their strength. The nacelles up top are pressurized so that the salt air doesn't get into the components that are up there and compromise them through over time. And they're designed, and you can see this on the picture on the left. They're designed for safety, accessibility, and crew transfer. So that there's a lot of components that go into just those features, so that the crews can board these things safely. They all have a drivetrain that's deviates a little bit from a lot of the land-based conventions, which means they have direct drive generators. They send the shaft power at very slow speed to a generator and convert it immediately to electricity, or through a gearbox that goes to a medium speed generator that's running at hundreds of RPM, not thousands. And then there's a specialized workforce training to operate and maintain those technologies. So these turbines are getting larger, and I said, the larger the turbines, the better from a developer standpoint. But the turbines have to be matured as they get developed. So, but generally speaking, a larger turbine requires fewer installations, and reduces the number of turbines that have to be maintained, and it provides more energy because these turbines are taller, the hub heights are higher, and therefore there's more wind up top. And there's no real physical barrier that would prevent us from going even larger. The big trade-off is whether or not it makes sense to go larger and larger, or to industrialize the systems that are already developed and use the ports and infrastructure that were developed around those sizes. And that's decisions that the industry's working on right now. But by 2024, all of the major wind turbine manufacturers will be have a commercialized version of a 12 to 15 megawatt turbine that the developers will be tapping into those supply chains. So I'm going to talk about the components one by one. You'll see that the tower is one of the most prominent components, and it's a static structure that rises up from the seabed and holds the nacelle assembly up. It's a tube tower, and it's tapered, but it has to be structurally very strong to hold all of the thrust loads and all of the other loads that the turbine rotors are generating. It protects the workers because you can climb through the middle, and it's protected with the ladders. It protects against avian species that might want to perch because there's no perch places, and they're easier to maintain. So we can see that these cross sections are very large, and they can be manufactured. They need to be manufactured near an ocean. And if somebody could, I'm getting a little feedback. If you can mute, I'd be appreciative. Thank you. The yaw bearing is at the top of the tower, and I'm going to talk a little bit about that in just a minute. So inside the nacelle is the pretty much the components that are inside that big box that we see up top, everything but the rotor itself. And it contains the drivetrain, which is the mechanical pathway that converts the rotor torque to electricity. And it can have a gearbox, but typically it doesn't. And in the figure that's shown, it does not. This is showing just a direct drive generator that's mounted in front of the tower, and it converts the electricity right there and then sends it back to the power electronics that are in the top of the nacelle there. And those power electronics convert the variable wild AC power that comes off the generator. And then they rectify it into a quality AC signal that can be sent to the grid and used at grid voltages and frequencies. And so that's what the power electronics do, and that's all inside the cutaway that you see of that nacelle. The yaw system is mounted at the top of the tower, and it's a big turntable bearing that allows that entire assembly, the rotor and the nacelle, to rotate. And there's a sensor on the nacelle that determines where the wind is coming from, and it orients the whole machine toward the wind direction. And that keeps the power at maximum levels. And you can see that yaw bearing has to work pretty hard as the machine rotates around. It's carrying the bending and thrust loads of the whole system as it's also rotating. The exterior of the nacelle, if we get rid of the cutaway here, you see there's a few features on the outside that are relevant. There's a helideck that is used for helicopter landings. This isn't always used, but it's there, and it's available so that crew transfer can take place by helicopter. There's sensors that determine the wind speed and the temperature and the wind direction. And there's other sensors that can determine displacement. And then you see there's aviation warning lights that are required to warn aircraft. And those can be activated by radar, or they can be on all the time. but they need to be there. And then there's the just the composite nacelle enclosure that houses all the equipment and allows the equipment to be protected from the marine environment. So now we'll talk about just the rotor. That's the part that I described earlier. It has 3 blades connected to the central hub that is connected to the main shaft, and that's all rotating. One of the key features of the rotor assembly is that the 3 blades are all connected to this hub by these circular turntable bearings that are mounted to the root of the blade. And those turntable bearings allow the blade to rotate at least 90 degrees. And that's in one direction. On one extreme, the blade is parked and the rotor cannot turn. In the other extreme, the blade is pitched to power, and it can turn and generate a lot of power. And then on a finer tuning, the blade can modify its angle to adjust power so that the power never exceeds the maximum power of the machine. Each of the blades, though, has this independent pitch control. Normally, they're pitching at the same rate at the same time, and you wouldn't know that they were not connected to each other. But in the event of an emergency, any one of the blades can shut the machine down by itself by just simply pitching to a non-power position. And that makes the machines very, very reliable because we have triple redundancy. This is what a blade looks like. And this is kind of a historic view as well. I have at the bottom what the old 7-meter blades used to look like in the 1980s. These were the basically all the European machines had this style blade. These worked well, but they were not optimized. And these come from our colleague Ken Thompson, who first published this picture, but I've used it a lot. In the evolution of wind turbine blades, they become a lot more slender. And the above blade, which is now representative, not precisely, but representative of the larger machines, you can see how much slender they are, and they have much more sculpted, tapered shapes to adapt them for the loads that are coming in and to maximize energy production. If we just scaled up that 7-meter blade to 107 meters like the GE blade, the weight of that blade would be so large that it would fall off the hub itself just on its own weight. So a lot of technology has gone into the development of these larger blades, which are made of mostly fiberglass, but now we're introducing carbon fibers to stiffen the blades some. And usually the blades are a combination of carbon and fiberglass and balsa cores that are used to stiffen the panels. You can see a cutaway on the right side of kind of an earlier version of one of the blades, and most of it's hollow inside, but you see that does have these shear webs that prevent the panels from buckling. That's a typical section. So now I'm just going to talk about the substations. This is where all the power is aggregated. The turbines are all connected to one of these substations. And at this substation, it collects power at about 66,000 volts from the turbines, which have their own transformers to bring it to that level. And then from that level, it's stepped up even further to about 220 kilovolts. And then it's aggregated together and sent to an export cable that is buried in the sea and brought to shore where it can be connected to the land-based grid. The substations are using the same structural substructures as some of the machines themselves and attached to the seabed. It's all technology that was developed from the oil and gas industry in being able to attach these heavy substructures to the seabed. Floating substations are on their way, but they're nascent and will have to be developed, and they will be a slightly different animal. Some of these machines, some of these substations also have temporary sleeping quarters, so if crew have to stay out there, they can. And then finally, I have this comparison. So as we wrap up the what's above the water. This is what these are 3 machines. One of them is a fixed bottom machine, the one on the right, and the 2 on the left are floating machines, and they look very much the same. They use the same turbines, but they have different substructures, and depending on the substructures, they can look identical, and you might not even be able to tell them apart. So the one in the middle is a spar that was installed by Equinor, and it is a floating spar. So now I'm just going to wrap up from a big picture standpoint. We now have a national goal in the United States for 30 gigawatts by 2030. This was set in March, and it's really commensurate with the policy commitments that have been made by each of the states. The wind resource, which is a very important parameter for us to understand and to measure, is determined by many factors, but wind speed is probably the most important one. Wind direction is important, and we need to know the time of day and the seasonality of these wind measurements. And I've talked a little bit about all of that. Offshore wind turbines are derived from land-based turbines and are adapted, and they're adapted to the marine environment, and so therefore they are bigger and they're protected from the salty air. Offshore wind turbines are getting increasingly larger because larger turbines are more economical, but we're right now reaching a new plateau of 12 to 15 megawatt turbines that will be deployed over the next decade. And the industry is building infrastructure to accommodate that size machine, both in the supply chain and the manufacture of these 12 to 15 megawatt components, as well as the ports and harbors and vessels that go into installing those machines. And when you look at these machines from above the water, they're very similar between the fixed bottom systems and the floating systems, and we'll be likely putting in both kinds in the next 10 to 15 years. And that's the end of my talk, and I'll be happy to take questions at this time.
Great, thanks, Walt. We really appreciate all that information, and we've been collecting some questions in the Q&A. So I'm going to go through some of those now. To start, folks are wondering, what are some of the ways to reduce maintenance costs for offshore wind generally?
Yeah, that's a good question. We're just getting started in this country, but we do have a lot of insights from our European partners who have encountered some of this. We know a lot about how to maintain wind turbines from land-based wind, but a big part of the cost is to access the turbines in the offshore environment. So it's very important that we know more about the nature of the failure and the maintenance that we're going to perform before we go out there, because it costs a lot to send somebody out to say, look at a machine. So remote sensing and remote data collection and diagnostics is going to be very important, so that a lot of the troubleshooting can be done before anyone even approaches a wind turbine. And then once we get out to sea, the use of robotics and machinery, drones that can look at the systems without a human having to climb up will be very important as well. And these are all nascent technologies that are being developed, and but show very high promise for lowering maintenance costs.
Great, and actually to build on that, we just had a question come in asking how the buffer and safety radius is determined for a wind turbine. So 12 for like a 12 or 15 megawatt turbine, how is that determined?
I think this could be answered a couple different ways. Are we talking about spacing between the turbines, or are we talking about how close can one get to a turbine? Because necessarily no setback from the turbine itself. They have to go up to the turbine to maintain them, and a ship or say a fishing vessel could at least theoretically go right next to those turbines and go up under them, because the blade passing is 30 meters above the water line. But that would have to be taken into account. And I don't know if any setbacks have been established by the Bureau of Ocean Energy Management that regulates offshore wind projects. If the question is more about spacing the turbines apart from each other, that is also being negotiated, but it's a trade-off between the length of the cable that's necessary to connect all the turbines together and the wakes that are being generated by the turbines. So if the turbines are close together, they're going to generate higher wakes and have more interference, especially for the downstream turbines. So that has to be all taken into consideration. In the Massachusetts wind energy area, the spacing of wind turbines has been established at 1 nautical mile, which corresponds to a little over 8 rotor diameters if you're putting in GE machines. So that's pretty conservative spacing for wind turbines, and so it should help in the power generation as well.
Great. There were a couple questions about offshore wind development in the Great Lakes and the recent approval of the Icebreaker project. And I'm hoping you can talk a little bit about just generally offshore wind development in the Great Lakes, but then also, what technology you see being used in that setting.
Yeah, so the Great Lakes are unique because they have freshwater ice, and also in order to access the lakes, you have to bring ships in through the locks of the St. Lawrence, which are limited in the beam width mostly. And so the large turbine installation vessels that we're familiar with in European wind farms, and we'll soon be familiar with in the Atlantic installations, those ships can't fit into the Great Lakes. So the Great Lakes will have to have its own infrastructure that lives on the lakes, and it may be lake dependent. So Lake Erie is a shallow lake and it freezes harder than the other lakes. It will have its own requirements, and that's where Icebreaker is. It's off the coast of Cleveland. In Lake Ontario, it's mostly a New York owned lake, that will have lighter ice, but it's deeper. So the technologies in Ontario will have to be floating, and whereas in Lake Erie, they'll have to be fixed bottom. And each of these situations requires a different take on the infrastructure that will need to be built in terms of the ports. There's a lot of new technologies that we're seeing that are promising for the Great Lakes or other areas where some of the other foundation types might not work, such as float out systems that don't require heavy lift vessels. And it's yet to be seen what the optimum technology would be for the lakes. But there's several options on the drawing board, but very few that have been demonstrated in practice yet because of the ice.
Well, we actually had a question come in about vessels and the Jones Act, and if you see the Jones Act potentially influencing what types of technology will be used here in the US, or if you see it as a big barrier for offshore wind generally.
I would say it's a challenge, but we're already seeing ships being built in the US that are compliant with the Jones Act. And there's no reason why the US couldn't build its own ships and have a fleet of ships that are available for not just installation, but maintaining the fleet that's going to be built. So that's one option, but there's no reason why the US has to do this the same as Europe, and even Europe has the same challenge because most of the ships that they built for the first, say, 33 gigawatts of offshore wind, most of those ships won't work for the 15 megawatt machines. So they're going to have to build new ships as well. So the industry is at kind of a crossroads where we're moving toward just building larger ships and scaling up the technology. But there's also the option to start looking at technologies that don't require such heavy lift vessels so that we can maybe more efficiently install some of these machines and maintain them.
Great, thank you. We had some questions come in about the difference between wind speeds and seasonal variations between land and offshore, and if they're different, that usually wind speeds on land are lower in the summer and higher in the winter, and if it's opposite in offshore situations.
I don't think we. First of all, that's a very regionally specific question. It may vary, so I wouldn't say there's one answer for all. There's definitely differences between the offshore characteristics and the land-based characteristics whenever you at a particular site. In California, we see capacity credit that is about twice as high for the offshore wind resource than we see for the land-based resource, because the winds blow more steady and more consistently offshore. And we may see some of that same trend in other areas but we haven't really looked at it extensively in the other areas. But I think the short answer is that they do vary, and in some cases we've seen better load matching or better matching of the peak wind speeds with the peak loads in places where they're building or they want to build offshore wind.
Gotcha. Great, thank you. So we've had a couple questions come in about ocean life and birds, and I know, Walt, that isn't your expertise necessarily, but do you have anything to say there? I'll just say that we actually have a webinar series happening with our wildlife group through the SEER program, and we can provide that information to folks when we send out the Q&A answers. So just to preface that before you dive in, Walt.
Yeah, so I will probably be brief there, but we haven't seen a catastrophic threat to either birds or ocean life. There's strong evidence that the fish and can thrive in some cases in the wind farms, but so it doesn't, we're not worried about that, but there's more of an impact to the fishing industry than there is to the fish. When it comes to marine mammals, we've seen impacts, especially during construction, where the noise could affect the marine mammals, and so we take very strong precautions against producing noise that could injure their hearing or even threaten their lives. And so that's all taken into account during the construction, and it has to be very carefully monitored. And birds, the same way, we would be very careful about where we sited the machines and how they would impact flyways and things like that. I'll leave those questions for others, but generally we're, on land, wind turbines aren't the major threat to birds. Glass buildings and house cats and cell towers and automobiles all have higher threats, but that doesn't mean that we don't that we discount the possibility that we could affect the avian communities as well, and we take precautions in that light as well. And I'll leave the rest of that to the other webinars that you mentioned.
Yeah, and another great resource is the International Energy Agency Task 34 REN website. There's a lot of great state of the science briefing sheets if anyone is interested, and we can send out that link as well. We had a question about control strategies, and if you could talk about any, any control strategies that are, commonly used at the farm level. So just wind farm controls. If not,
anything specific on controls? I mean, it's a big field. I will say, unless there's a specific part to that, I will say that controls and the advancements that we've seen in controls over the last decade have allowed a lot of the innovation that we're seeing today on the large wind turbines, and they've allowed us to or to reduce the weight of the machines by sensing loads before they happen in some cases, and allowing stabilization of floating platforms, for example. So that's a huge thing. On a farm level, we're seeing control systems implemented that allow us to actually operate the wind farm as one unit rather than individual turbines. So we're maximizing the power output of the entire system by having the front turbines that see the wind first steer the wakes away from the turbines that are behind them, so that they don't so that they experience better energy flow, and things like that we're seeing that are still in the experimental stage in some cases, but think of the wind turbines acting like a flock of birds rather than just a bunch of random turbines all independently out for themselves.
Great. Well, thank you for helping us answer that very broad question. I think we've gone through a lot of questions. You've answered a lot of questions for us today, Walt, and we really appreciate your time. And I think we're going to go ahead and wrap up the webinar. I just want to say thank you to everyone who joined us today. And there was many questions about if this recording and presentation will be available. And yes, it will, but we will be both posting it to YouTube, NREL's WINDExchange website, and sending it to the group that signed up for this webinar. That will take about 7 to 14 days, but we will try and get it out to you as soon as possible. I just want to thank you again from the National Renewable Energy Laboratory for joining us today. And I think we will wrap up with that.
Thank you, Liz.
Thanks, Walt. Really appreciate your time.